presente, vamos a dar comienzo a esta charla. ¿Se me escucha bien?
Sí, perfecto.
Sí, Marta.
Sí.
Sí.
Bueno, buenos días a todos, buenas tardes a todos. Les damos la bienvenida a todos los asistentes a este tercer y último encuentro de este año 2022, de este ciclo de charlas abiertas, que lo hemos denominado On Demand o a la carta, organizados por el capítulo argentino de la SPWLA. Mi nombre es Marta D'Angiola y sigo presidiendo durante este año, ya es el tercer año, orgullosamente este capítulo. Formamos parte de un grupo de evaluadores de formaciones de alto nivel profesional, pero fundamentalmente lo que nos une es que somos un excelente grupo humano. Si quieren indagar un poco más sobre nuestras actividades, los invito a visitar el sitio www.spwla.org, y además tenemos una casilla de correo a través de la cual nosotros vamos enviando toda la información. Y nos mantenemos conectados y allí se gestionan los permisos y los links para poder acceder a nuestras charlas. Como toda organización, tenemos la necesidad de formar parte de una organización global. Por lo tanto, invitamos a todos los que puedan a unirse como miembros. Existe la posibilidad de sumarse como miembro profesional y nosotros, como pertenecemos al Grupo 2, junto con Colombia y otros países de Latinoamérica, nuestra membresía es el 40% de la membresía de otros países. Nosotros normalmente se pagan $100 por año, pero la membresía de los países de Grupo 2 es de $40. También existe una posibilidad de asociarse o de sumarse de una manera gratuita, formando parte como afiliado, ¿sí? Entren en la página y van a ver que se van a poder asociar a ese y sí, adhiéranse a nuestro capítulo. Y bueno, también está la posibilidad para los estudiantes, y algo que no hace tanto, que fue recién desde el año pasado, porque la membresía para estudiante era de $15 anuales, y a partir del año pasado es solo de $6 anuales. Hoy, ahora vamos a invitar al doctor Alan Bischoff, que nos va a acompañar con esta charla. Voy a darle paso al micrófono a Camila Juan Suriano de Practia, quien oficiará de moderadora en esta charla. Camila es una activa colaboradora en nuestro capítulo, especialmente en el grupo de media. Camila, el micrófono es todo tuyo.
Gracias, Marta. Bueno, la charla de hoy podemos decir, como dijo Marta, que es una charla on demand o a la carta, porque a principios de este año luego de hacer una encuesta de temas de interés, este tópico fue uno de los más votados. Cumpliendo con lo prometido, invitamos al doctor Alan Bischoff, quien disertará sobre el tema En busca de recursos geotérmicos profundos en cratones cristalinos. Alan Bischoff es un geocientífico de energía que combina la experiencia obtenida en múltiples disciplinas, incluida la reflexión sísmica, el análisis de cuencas, la estratigrafía, la vulcanología, los sistemas ígneos y la tectónica para investigar el potencial de las perspectivas geoenergéticas. Se considera entusiasmado con la exploración de recursos geoenergéticos como la energía geotérmica y las nuevas tecnologías de geoalmacenamiento de CO2. Trabaja actualmente con el Grupo de Geoenergía del Servicio Geológico de Finlandia, principalmente desarrollando proyectos científicos y comerciales diseñados para aumentar la absorción de energía geotérmica en los países nórdicos y en todo el mundo. La experiencia previa incluye 5 años trabajando como geólogo de exploración de petróleo en alta mar en Brasil, exploración de minería de oro en Nueva Zelanda, y más de 7 años como investigador académico en la Universidad de Canterbury, Nueva Zelanda. Actualmente se interesa en comprender cómo la porosidad natural y la permeabilidad de las rocas cristalinas pueden crear oportunidades para desarrollos geotérmicos asociados con zonas de fallas de la corteza y sistemas ígneos antiguos y modernos. Les recordamos que la charla tendrá una duración aproximada de 40 minutos y será en inglés. Las preguntas que surjan las pueden ir escribiendo en el panel del chat, en español o en inglés, es indistinto, y Alan las contestará al finalizar. Si alguno se anima, puede activar el micrófono. Alan, you can start with your presentation. Please go ahead.
So, good morning, everybody. No, bom dia, buenos dias, or huva huamenta. How do they say here in Finland? Struggling so much with this language still. I guess lots of you that are today in this talk perhaps are in Argentina, which is probably the middle of the day. Here we're going towards the end of the day. And it's an enormous pleasure to be talking with all friends and see new faces as well in this talk, where we're going to explore a bit of the petrophysical characteristics of crystalline rocks and how can we actually start to find better prospects from deep geothermal exploration away from volcanic areas. Just confirming that, is everything going okay? Can you hear me well? The presentation is going?
Yes, Alan.
Maybe Marta?
Perfecto.
Perfecto, vamos entonces. So the presentation outline, I split this talk in 3 topics. In the first topic, we'll talk about the rationale. What's the reasons that we need to chase deep geothermal resources in crystalline cratons? Why can we just keep doing what we have been doing to provide energy for our society? And then we will look at some deep geothermal prospects, aiming to reduce the risks while we can increase the rewards. Now, we know that geothermal exploration, when we go in deep, it becomes very expensive, despite of the fact that we already have a bunch of technologies that could provide this energy for us. We need to reduce the cost. Drilling costs is one of the main reasons that we are not yet providing geothermal energy worldwide. And also now we need to start to understand how can we better define the resources that we have away from volcanic areas. And then in the third part of the talk, I will show you some of the data that we have been investigating in a deep borehole that was drilled in northern Finland. It's called the Kolisma Deep Drill Hole, where we have been finding really interesting petrophysical features there in terms of crystalline reservoirs. And this is probably going to be the main aspect of the talk. Now, I will show you some different pore networks that are related with crystalline rocks, mainly granites and mafic ultramafic rocks. And probably as much as for me, it is a surprise that we can have such a great network of pores in crystalline rocks that usually are now considered to be low porosity and permeability. But before I open this talk, I really would like to acknowledge the work of several people that have been also chasing these deep geothermal resources. So I'm not alone in this walk. Of course, this is a big challenge for several geoscientists. And here now I put on the screen just a couple of names that quickly remind that they have been doing similar work and we are collaborating. So thank you very much for the work of everyone. A few words about myself. I was born in Brazil and I studied in the University Federal do Rio Grande do Sul in southern Brazil, from 98. in the last millennium until 2004. And as much as most of the geologists that I know, we carry a lot of rocks, and that actually was a really good time in my career. Carrying rocks, learning by going to the field, it was a really great experience. And straight after I finished the geology school, I started working in Petrobras. Now here it's me, several years younger, working in an oil rig offshore Brazil. And I spent a lot of time looking at seismic data and looking at sedimentary reservoirs, but also I work in the marine geology department, mapping geohazards, so that a lot of marine geology made part of my background. In 2010, now I made a big change. I visited New Zealand and stayed 12 years there. Now, in that journey, I worked with gold mining exploration, starting to move slowly, moving away from the sedimentary rocks, which was my initial passion. Now, but also did other activities to keep maintaining myself in New Zealand. For example, one of the nicest ones, I work as a glacier guide. Unfortunately, this glacier here pretty much disappeared. The ice that I'm standing here, there is nothing else. It's just a bunch of rocks. But it was a great stage in my life that I could explore the amazing scenarios in New Zealand. And then in 2015, I went back to the University of Canterbury, and I started to study volcanic systems. So moving even further away from the sedimentary geology, I end up with these beasts, and that really became the passion of my life for several years. Now looking at these volcanic systems and seismic data, and I think we did a great work studying volcanic reservoirs. Now today I'm living here in Finland and I work in the geoenergy team of the Geological Survey of Finland. It's been 1 year that I'm living here in the city of Turku, and this is how the city is right now. Now, this is not my photograph, but if you go outside, you're exactly gonna see this. This is the sea, partially frozen, lovely weather. And that's my daughter going to the school. Now, we need to put crampons in the little thing. But now I learned that in Finland, now the seasons, they are really well defined. And the spring is lovely. The summer is really beautiful. So I recommend you guys, if you have a chance to visit Finland, it's a great country. And then starting with the initial part of this talk, discussing about the reasons to chase the deep geothermal resources in crystalline cratons. Why can we just stay in the easy part of geology? So there are several socio-economic and environmental reasons that we should start to look for these resources now in a broader scale. If you look at the world map that I'm showing here on the screen, now all the areas that are marked in red are mostly tectonic boundaries, the plate boundaries where we have high heat flow. Now, in these high heat flow areas, every little red dot that you see here is already a geothermal plant that have been producing electricity. So we have lots of them around the world, but that zones are very narrow and very confined to certain areas of the globe. Now, in contrast, what you're seeing here in the pink color is the crystalline cratons, which make large parts of the continents. So this is one of the reasons that we should start to get away from these high temperature areas. Because if you look at for example, the crystalline rocks beneath Finland, from that interval from 4 to 7 kilometers, there is a huge amount of energy stored on that rocks. And that could help several countries, especially for the heating demands of the countries. In the case of Finland, it could help the country to provide the district heating demands for over 100,000 years with that energy that we have under the ground stored in crystalline rocks. And then we will see why we are not doing that, why we are not taking that energy. And also we say now that most of the countries, they are in this fight now for the energy transition. And Finland have started this quite almost 10 years, almost 20 years ago, that the country is phasing out now from fossil fuels and increasing other types of energy. But you don't see any geothermal here now. But the decarbonization of the country is huge still. Now there is 40% of the energy of Finland that's still being produced by oil and gas now and coal that the country is aiming to find for alternatives. So there is a huge market that's being opened now for the geothermal energy. And this is what we know we can provide as geoscientists. Very few words about climate change. Now, I really like this graphic here because in one axis we're seeing the time and the time change in scale. Now, here first we're seeing millions of years, then thousands of years, and then tens of years. And the temperature is still the same. Now, the temperature have been decreasing all the way from the Paleocene. Everyone knows about that. And this is related with the uplift of the Himalayas, now sucking CO2 out of the atmosphere. Then we enter in a stage here of the glaciations, really well marked by Milankovitch cycles. And finally, now we enter in the Holocene, which is a very stable time, very stable period of time. And that's where our civilization started. Now, and when people talk for a geologist now, why do I care about climate change? And climate always has changed. And even in the Paleocene maximum here, we have forests in the Arctics, and that was true. But sometimes we forgot that the Holocene is a very stable period of time, and the predictions now is telling us that we are losing that stability. And perhaps this is the most critical thing that we need to consider. And it's not just about oil and gas. There is several activities that now release greenhouse gases, and that will influence the climate. Now, not in a dangerous way that not going to have life anymore on Earth, but the stability, the predictability of the Holocene. For example, the seasons, this is what the climate scientists are really worrying about. And I like to share this graphic because for me also was an open mind to understand what they are talking about. We always, as a geologist, who cares, have been changing all the time. But it's more about the stability of the Holocene that they are worried. And for those that look at the IPCC report, this graphic is quite nice. And especially for petrophysics, we love to model things. We love to put a lot of numbers and make models and see what they tell us. So the black curve here, that you're seeing is the temperature that have been observed, since the Industrial Revolution. And the blue one here is a simulation of the temperature if they only consider natural causes. And that's the simulation inputting the human emissions, the CO2 emissions in the atmosphere, and the match is really well done. So usually, as petrophysical people, when we have a good match like that, we make interpretations that this is the truth. And I'm not saying that that's the truth, but it's just something to think about. But that's not the way, that's not the aim of our talk. Also, why do we need a geoenergy paradigm shift? It's a lot of talk in the last decades about oil peak. And suddenly people, because we have more technology, we find more ways to extract oil and gas. Now we have been delaying that. But the forecast is not the best, guys. We have 52 years of oil, 54 years of gas, and 110 years of coal. And the thing is, these are amazing resources that someone already said, that wasn't me. If humanity didn't have oil and gas, we will have to invent it. Because it is such amazing resources, and we can't just, in 100 years exhaust that. And every time we go for deeper and for more challenging environments, the costs are higher. So we can't just take everything we have. We need that to find the new types of energy. And this is where I believe the geoscientists have an extremely important role in the society. 10 years ago, everyone that was graduating and want to work with energy, we will go for the hydrocarbon exploration, and that was my path as well. And I'm very proud that from what I learned, researching from hydrocarbons, it's an amazing school. Or we thermal, which is very, very small comparing with what hydrocarbons have been providing us, for the last century. But today, we have a new word that's not so well defined. Is what we call geoenergy. Now we start to put all the types of energies that can be, extracted, stored, or disposal of waste of energy in the subsurface. All of this, it's being considering now as a large branch of what you call today geoenergy. And then beyond what we can use, for exploration of oil and gas and geothermal, which have several types of geothermal energies that could be considered, inside of the geoenergy, we also have this technology that we can store energy under the ground. For example, compressed air storage. You use renewable energy to increase the pressure inside of a reservoir when you have wind power, and then you can start to use that power from the pressure of the reservoir when you don't have wind to generate power in a turbine. This is one of the things that you can use the underground geology for storing energy. Hydrogen storage is a really hot potato at the moment, so geoscience play a very important role in understanding where we can find these trap structures here to store hydrogen, which is very, in certain way, very similar with the petroleum system. And then also those new technologies for disposal of waste of energy. For example, CO2 sequestration. This is a geothermal plant in Iceland where they are storing the CO2 in the form of carbon mineralization. Now, basaltic rocks and ultramafic rocks, they can react. They react to CO2 and they form calcite or magnesite, and they stay stored underground. And here in Finland, there is an amazing nuclear waste disposal that is almost 500 meters now, a series of caves that have been dug underground, and a huge geological study now to understand the weakest zones of the rocks have been done to try to characterize where is the best place to store this nuclear waste. And why do we put all these types of energy in a single name that's geoenergy? Is because the reservoir properties of the rocks needs to be very well understood. Now the fluid flow dynamics, heat and mass transfer, and also all the physical, chemical, and geomechanical reactions that are going to happen in that rock. So now petrophysical guys and geologists in general, in geophysics, they play a fundamental role in all this type of geoenergy. Now technologies that are mostly emerging now in the 2010s from now. Very brief introduction. Now we go for the second part, where we try to understand, the reducing the risks, why we can increase the rewards of the deep geothermal prospects. Large-scale production of geothermal energy rely on two main factors. Now, heat. We need to have heat from the ground, and that's why we look at the volcanic areas, and we need to have permeability. Now, here there is an example of geothermal gradients from several places in the world. Now, Italy, where we have active volcanism, the geothermal gradient increased really high, temperatures going in quite shallow depths. And the same where we have the rift zones in France. Now, the mantle comes closer, the heat flow is much higher in that region of the rifts, and then the geothermal gradient increased very fast. These regions, we are doing pretty well there. But what do we do with regions like here in Finland, where the geothermal gradient is much lower, and then we need to drill much deeper to find resource? For example, now the subsurface in Finland, now to achieve about 100 degrees, now we need to drill 6 kilometers. Now that is a huge amount of rocks that we have to drill now to get that resource that here in Italy, now you could get in just a couple hundred meters. Another challenge is as you go lower in the crust, now the porosity and the permeability reduce. So then the permeable zones, they become scarcer and they become harder to find. And perhaps this is one of the main challenges that we have now. Where can we find these permeable zones that will provide fluid flow circulation in the rock, that we can take all the terawatts of energy that is stored in crystalline rocks? How can we find that? Now, perhaps is the main challenge. And I will try to give you some ideas now what we are looking at now. Here in Finland, as you saw now in this graphic here, probably one of the most challenged places in the world to find geothermal energy. Now, and I think the history of geothermal, the geothermal industry in the country has been doing amazing. Now, because the country, now they use 26% of the energy of the country is for space heating. Now, so we can use directly very low temperature now resources to warm up our houses. Now, and this is what the country have been doing since the 70s. Now, this graph here is showing the number of geothermal heat pumps that have been installed in the country. Now, here from 1970 to 2021, and you see the increase is exponential. Now, there is several houses that have been putting this shallow geothermal systems to warm up the house. And today, together, geothermal and air heat pumps, they provide 25 petajoules of energy. Now, this is 2% of the total energy of the country. It seems nothing, but consider that we are in one of the most challenges environments now in terms of temperature. It's very cold here in the winter, and it's doing really well. Now, there is over 150,000 geothermal heat pumps installed today in Finland, and over 20 million households globally. It's a market that took over by itself. Now, I don't think we need to do much more about that. There's a lot of research ongoing now, but it's a market that's very well established. Now, as I say, now how can we upscale that? Now, the uptake of geothermal energy in crystalline cratons, and start to provide district heat, start to provide energy for large buildings. What have been done here already in Finland? Now, one of the things we can do is increase the number of boreholes. Now, if rather than have a single borehole, you have several of them. And there is this is what we call a borehole field. Now, a geothermal borehole field. There is 45 in operation in Finland today. Now, and here you can see the number of boreholes that we have in each of them, and here the average depth. This is what we call very shallow geothermal exploration. And I'm going to show you what have been done here in the Aalto University, where they have 74 boreholes producing geothermal energy. This is a work that have been done in collaboration with GTK, and this guy here, Sami, is one of our geologists. Now, he's a really expert modeler. Now, fortunately, now here in the area that you're seeing where we have the borehole field, every one of these red dots, now the red circles, they are the location of the boreholes, but there is 6 of them that we have a permanent measurement of the temperature. Now, we are monitoring the temperature of these boreholes for several years. Now, here's the graph that you are seeing, that the models that Sami have been doing, now showing the modeling, now the calculations, now show the how much energy we are injecting back in the reservoir during the summer, and then when we start to take that energy now to warm up the buildings during the winter, the temperature go very low. And this curve that you're seeing now predicting by 2040 now is the modeling, and the black one is the observed. Now, so really nice fit again between the modeling and the observed, showing that our predictions, they are quite nice. What's the one more thing that I would like to say is the annual energy that they are producing there is about 1,600 megawatts of energy in 1 year, and they are putting back 320 megawatts of energy have been putting back in the reservoir now when you cool down the building. Now, this is covering at the moment 95% of the energy consumption of that buildings. But as you can see now, there is a huge mismatch between what we are extracting and what we're putting back in the ground. And that's what the graph here that Sammy produced show, that after a while, now the energy gonna start to become below zero. Now this is zero in temperature and it's gonna start to freeze. So this means that even if we increase the number of the boreholes, at some point, now if we don't put energy back in the reservoir, we're gonna have problems. Another one of our modelers here also show that increasing the number of boreholes, now it can be very damaging because one borehole, it takes the energy from the ground and influences the borehole next to it. Now this is a series of graphs showing how much energy you're gonna produce when you have more boreholes. For example, you have a borehole field with 10,000 boreholes and the spacing between the boreholes is 10 meters. Or if the spacing is 50 meters, you see that the energy drastically is lowering as you increase the number of boreholes. Now this means now at some point we're gonna freeze down the system there. Now, so what is the solution for that? Increasing the number of boreholes, it gives you how do you say, you can breathe again, you have a little bit more of time to think what you're gonna do. But at a certain point, we're gonna have to find a permanent solution. This is where we enter to the, this topic, that is how can we go deeper and how much actually is beneficial for going deeper. Another one of our modelers, Caio creates 3 models now in northern Finland, central Finland, and southern Finland, and applying several thermogeological parameters to try to understand, how the ground will respond when you have deeper boreholes at several depths. But one of the things as geologists, we don't consider too important is the engineering parameters, but they are really, really important. Is what type of pipes do you use in your system? Now, what type of collector do you use? And mostly, how do you circulate the fluid inside of a borehole? If you circulate faster, you will get more energy faster, but you reduce the energy of your borehole very quick. The results are quite okay-ish, let's say, but they're still quite small. Now, if you take a 600 meters borehole and you increase to 300 meters, there is almost like 10 times more energy that you can extract for that borehole. But again, because these models here, they don't consider permeability, they don't consider water coming inside of the borehole from the rock, they only consider the energy that you can extract around of a borehole. Now, then they show that very rapidly, now in the first 1 or 2 years of activity in the field, you will reduce the amount of energy that you can extract quite significantly. So again, now going deeper have limitations. And now is when we always need to talk about how much does it cost. This is how decision makers, they think. Shall I go for a shallow geothermal system? Shall I go for a deeper one, or shall I don't go at all? Now, when you look at a borehole field with 70 boreholes like the one in Espoo, the annual energy that we can produce there is about 1,600 megawatts. And the cost of drilling, I'm not talking about the cost of the system, just the cost of drilling, is about 35 per meter. No, 7,500 euros. Now that it will cost to drill that 70 boreholes at shallow depths. One single 3 kilometers borehole can produce just a little bit more of energy, but the cost goes for almost 5 million. So the decision is very easy to make here where you go now, especially if you know that the results now it's very similar and you're going to have a decrease in the energy quite quickly. What do we need then? Now, these systems that I'm talking now is only based in conduction. It's conductive dominated systems. Now you have a borehole that you inject water in the sidewall, is a coaxial system. Now you inject water in the borehole from the sides of the well, then it's warm up, now in contact with the rock, and then you produce the hot water inside of the borehole again. You see, there is no permeability, there is nothing that can extract the heat from larger areas. Today, they have been calling this AGS, Advanced Geothermal Systems, and there is several types of designing. You see the most crazy things, inclusively, there is some geothermal pilot projects ongoing in Canada and Germany, that they have a series of boreholes that they interconnect, and that seems to give much more energy. But again, now, if you go back for the costs of drilling, how do they gonna do the system, make it economical? I still not knowing. In contrast with that, now looking at what geology and what nature can provide. Now, some of the models show if you have an increase in permeability from 10 na minus 18 to 10 na minus 15, which is still very low permeability. This is more or less 1 millidarcy. Now, you have almost 20% increase in the heat production compared with a exclusively conduction dominated system. It's already telling us that permeability, now fine permeability in the ground, it is the way to go. And this is what they're trying to do with the enhanced geothermal system, now cracking the rocks there to start to produce energy from larger areas. There is where you come now to discuss a bit about the crystalline rocks. Now, this graph here showing one axis the permeability and here the porosity. And we have several types of rocks that are already now proved geothermal reservoirs in several areas in the world. And we know that volcanic rocks that are nice and porous and permeable, and sedimentary rocks, they have the highest chance to have good reservoirs. When we have fractures also, you can have a good permeability, especially. Now, vuggy carbonates, and then the crystalline rocks are poured them down there. Now, pretty much no permeability and very low porosity. Our challenge now is to show a new paradigm now that we see that crystalline rocks also they can have good porosity permeability now when under certain conditions. Now the graph here is in the same scale. Now you see porosity and permeability are in the same scale. And now if you consider just crystalline rocks that are not fractured and are not altered, now they are fresh crystalline rocks, we need to agree they are very low porosity and permeability. But new data showing that as you start to increase the number of fractures, and especially increasing the alteration of the rocks, you start to dissolve certain types of minerals. Now the porosity and the permeability together, they start to create reservoirs that have the same petrophysical properties, now at least in terms of porosity and permeability. I'm not going to talk about pore connectivity yet. Now, but they have very similar petrophysical property as sedimentary rocks, and this gives us good prospects. Now, we should start to investigate how a granite, very interlocking crystals like this one become this guy here. And this is a rock not too far here. This is here from Finland, and we can see here in yellow, this is a pore created by dissolution. The question then comes now, where can we find these crystalline reservoirs? We know that they are not everywhere. No, because most of the data show us the crystalline rocks, they are not permeable, not porous. But there's two situations that I would like to highlight. One is already very well known by the geothermal industry and even the oil and gas industry. Now they look for fault zones sometimes, they want sweet spots that can have higher permeability by cracking of the rocks. As I say, very well known in fault zones. As you go closer to the fault, you have more damaged zone of the rock, you increase the permeability. But then, as sometimes when we are exactly in the core zone of a fault, now you can have pseudotachelites, for example, that is glass, and there is no permeability, there is no porosity at all. The message here, we are in a much more complex system than just looking at a normal porous sandstone, especially like a nice and clean clastic sandstone in the top of an anticline. Everyone wants that, but no good luck with that. No, this is already gone. And now we need to start to look at the systems that are much harder now and much more complex. But the rewards are there. Now, if you look at this graphic here showing now the fault permeability contrasting with the matrix permeability, when you are in this low zone here, now below 10 minus 12, which is 1 Darcy, and here 10 minus 17, more or less, now you only have conduction. Remember, the exclusive conduction systems, they have poor energy and they have high cost. We need to increase technology to be able now to explore these guys economically. But when we find permeable zones, especially if you also have, matrix permeability by dissolution, now increasing of secondary porosity by dissolution, you start to have convection. Now, and then from temperatures of 15 degrees in this model, you can go for temperatures of 55 degrees, almost the same, in the same environment. So inducing now convection and advection, now especially if it is natural, or you can increase the permeability of the system by stimulation, but not overcoming the strain of the rock there to create earthquakes, for example. Now that is the best situation that we can find in a fault zone. Less understood, and it's a topic that many people don't consider yet, is the proximity with igneous intrusions. This seismic image here offshore New Zealand show a large intrusion body now that creates several folds and folds now in the host rock. We know that by the intrusion volume in the crust, you need to create cracks that accommodate that volume. And that cracks and folds, they can be also a target, especially in crystalline areas that we have several intrusions of several ages. This graph here show in Iceland, now as you go closer to an intrusion, you start to increase the permeability. Now you're going again, 10 minus 13, 10 minus 12. And again, this is caused by mostly microfractures and mineral dissolution. Now, and here is another study that was done in New Zealand that you're showing an unaltered igneous intrusion versus an altered igneous intrusion. The shift that you have in porosity and permeability is quite high. Now you are coming from something really impermeable and really not porous towards something that starts to become, a reservoir. And the same happened in the host rock. The opposite happened when you have precipitation of minerals that can reduce the porosity and permeability. And this is very well known in any petroleum field. But that is the true situation that we should be looking for. And now I would like to show you some of this data from the Kolisma Deep drill hole, which is giving us an opportunity to look into the deeper crystalline crust here in the Fennoscandia. This is the study area now. It's almost in Russia. Now it's close to the border between Finland and Russia in the central Karelia region. Now is a zone where several mafic, ultramafic rocks from Paleoproterozoic age, they intrude into Archean gneisses and migmatites. Now, and also there is coeval post-orogenic granitoids. Now, everything that you see here in black is part of this mafic, ultramafic group of igneous rocks. Now, and here we can see really clearly now a geophysical anomaly. This is an aeromagnetic map now that connects the Koilisma ultramafic complex with the Narankavara. And the drill hole was placed now between these two complexes to test if what we are seeing here in the geophysical anomaly actually correspond. It is a link between these two now mafic ultramafic regions, and the drill hole did recover Now at the bottom, some mafic ultramafic regions. But also to complicate a bit more our situation there is a shear zone, a bit younger, that creates several faults. And also this that you see in smaller here is a series of dike intrusions, also Precambrian, very old stuff, you know, for us. But they could also have been creating processes that favor the porosity and permeability of the rocks that we see now. Here's a overview of the lowest part of the well. The well drilled to 1,700 meters and got stuck because the rocks were too fractured. Now here is a RQD that measure now how much fractures you have by meter, and some parts of the well was 100%. You know, this is the type of rock that they drilled there, and it's not surprising that we got stuck. The objective of that well was to go to 3 kilometers, but several problems, you know, for drilling make us to stop where we did, but we could prove that the mafic ultramafic rocks were there. And what brought me for this project, it was the very fractured characteristics of these rocks. Here you see the granites, coeval, same age as the mafic ultramafic rocks. And you can see here in the density log, there is a really nice correlation between the type of rock. Now, everything that you're going to see here in gray, this is, I will go through the rocks in a moment, but you can see there's a very nice correlation now between rock type and the density log. First type of rock that I want to introduce is the red one here, which is a very ordinary granite, boring as you can imagine. Just this little bit of mafics, plagioclase and feldspar and quartz. What do we do with that rock? It's quite really good. If you have a potassium feldspar, that's where the heat is being produced in the crystalline crust by decaying of the radiogenic minerals in that rocks. That is the source of the heat for us. Now, if you think like a petroleum geologist, this is our source rock. It's not so ordinary as it looks like. Another type of rocks then, everything that is in black here is the mafic ultramafic rocks. Now, mostly peridotites, pyroxenites, gabbros, and there is a lot of alteration to serpentinites. And the third type of rock, of course, there is much more complexity there. I'm just, simplifying to try to understand the reservoir properties. Is a rock that is, it is a granite as well, but is much more felsic. There is not much more feldspar, probably oligoclase. Mostly made of granodiorites, diorites, and tonalites. Which, for simplification, I'm calling everything here granodiorite, but the face of the rock is something like this, and it is what we have here in gray. As I say, the granite is not so ordinary as it looks like at first. Now, the fresh granite have several subphases. The first one that I want to introduce is what we call the fractured granite. You see now the type of rock in terms of composition is the same. Now, but this is a photograph of the drill core that you see, a very nice fracture network. And when you look at the CT image here, you can see that the network is disconnected. Now we can see the connectivity there, at least in the scale of a drill core. Now, but we can also see that you have several zones where that cracks, they are enlarged, and we'll see why. Now, the second type or the third type of granite that we found there, in terms of composition, is exactly the same, but we have cataclastic zones. Now, and then the introduction of cataclases there now create grains, and what we see here now is a CT scan showing that between the grains we have intergranular porosity. We start to talk the same language as petroleum geologists again. Now we are looking at intergranular porosity in crystalline rocks. Welcome. If that wasn't enough, to make our mind a bit tilted, now I introduced the fourth type of granite. That's the altered granite, where you can see several dots here that represent the dissolution of mafic minerals. And when you look here at the CT scan, everything that is in blue here, I forgot to say here as well, everything that's in blue is low density, so it's the pores of the rocks. Now, we measure that rock with 17% porosity, which is not something that you will find every day in a granite. Now, nice as well to see some epidot veins. It's what cross-cutting here, which start to give us an understanding of the process that that rock has suffered. Then just looking more in detail at the fractured granite. Now, as I mentioned before, the drill core shows that the fractures sometimes are really large. Now we are seeing these very large pores here. This is 800 microns in across now. And you can really see that these cracks are old cracks. This is not created by the drilling as some people might imagine. And obviously there is cracks that are created by the drilling. But when you look at the wall of the pore, you can see that there is now an alteration there, and there is some precipitation of minerals, and that tells us this crack is pretty old. You know. And here is really nice. We're seeing in 3 dimensions now the results of the CT scan, where you could see that the fracture networks are really nice and connected. Now, the porosity of this rock is quite small, it's about 4% now measured in the pycnometer. But again, remember now, you can increase quite small a number of porosity in crystalline rocks, but the permeability can increase a lot. I don't have the results yet of the permeability of these rocks, but I will show some of the results we do have. The CT scan at 11 microns show that 80% of these pores here, or these fractures, they are connected. We'd already give a good clue for us on how much porosity, how much permeability we will have there. Moving then to the cataclastic granite. Now, as I told you before, there is several, literally, now we can call that a clast. There is several fragments that were created by brittle deformation there. And here you can see that between the grains, you have a kind of a matrix that when you look here in the CT scan, that matrix is high density. Now is also what you see here, and mostly is precipitation of iron. Now that is not allowing that's intergranular porosity now can be completely developed, because you have a secondary precipitation of minerals that as well. But as you can see, the pore network is very different. Now you have cracks, but also you have several pores that are sometimes connected, sometimes disconnected. 77% porosity of this rock, and 75% of the spores, they seem to be connected, at least, you know, in the CT scan. But look at the geometry and the interconnectivity of the spores, how they are different from what you just saw now in the fractured granite that is nice and straight cracks. This is not. They have, you know, a much more random pattern. And that, of course, influences the fluid dynamics inside of the rock. Now, the outer granite, now we are seeing here, and there is a very high secondary porosity being created in this granite, mostly related with the substitution of mafic minerals, in this case here, pyroxene that's being altered to a chloride, and also no biotite that is being dissolved, that is forming now the secondary porosity. As I mentioned to you, 17% porosity. And when you look at the connectivity of the pores here in the CT scan, 75% of the pores are connected. Now, the only explanation that we can give for that alteration there, because we have, you know, substitution of mafic minerals to chloride, and also I mentioned now epidot, is that we have high temperature fluids percolating on that rock. The granodiorites, they have a very similar aspect with the fractured granite. There's nice and straight cracks, sometimes enlarged by dissolution, and sometimes you can see precipitation of sulfides now inside of the cracks too. Now, they are way less altered than the granite in certain places, but the cracks are nice and straight and quite well connected. And then the last type of rock, now the mafic, ultramafic, despite of the fact when you look at the borehole, they seem to have a lot of fractures and might be like really good reservoir. But most of it, now, we believe that they are created by the drilling, because this rock is really, really fragile. Now, and this is mostly relationship that we have, the alteration of olivine minerals here is being substituted by chlorite and serpentine. Now, this is creating a rock that is very friable. And even here where we can see now cataclastic rocks, like we discussed about the granites, between the grains is precipitation of serpentine and chlorite, which is make a rock with very, very low porosity. Now, it doesn't seem to be a great reservoir. It will be really good for CO2 sequestration because the reactivity of this rock. But I can't really say if that fractures, they will be open or not in the subsurface. We will need to test with packers to see if there is any permeability on that rock. As soon as I make a drill core like this and I put in the water, it just breaks in pieces and I can't measure anything. At the moment, now looking at thin sections and the CT scan, we can say zero porosity. So then let's discuss just a little bit about the origin of the hydrothermal fluids. We can see that the altered granite, like here we have a section that's about a meter of that granite, is mostly in contact with gabbro intrusions. And if you go very close to contact with intrusion, you see a lot of chlorite and epidotes. Now this is starting to indicate us that perhaps these gabbro intrusions, they are a little bit younger, and they are creating high temperature fluids that circulate water there and start to create secondary porosity. But other processes also happen now. We don't see only near to the contacts, but we also see near fault zones. Oops. I had another photo here that disappeared. I'm sorry for that. I suppose you have another photograph here showing leaking lines in the core, but you can kind of see them here. And in these fault zones, you have a lot of chloride and also epidotes. So both of the process, faulting and intrusions, which we discussed before, they both are bringing high temperature fluids. The really good question here now, in northern or in the Karelia region, the youngest hydrothermal events or the youngest faults that we know there, they are almost occur 1 billion years ago. If that porosity that we saw being created by the dissolution of minerals related with high temperature fluids occur 1 billion years ago, that means that it's still open. Now, this open scope for exploration of crystalline reservoirs in several areas that you think, this is an old and cold region. There is nothing else that but it seems that you can preserve porosity for even 1 billion years. And this is a really great finding of this work. Again, something have happened here in my presentation. I don't know why the graphic is not here. It's really a shame. I think there is some problem happening. You can see that my images are disappearing. But anyway, I almost exploded the time. Well, what I'm supposed to show you, I can actually, if you guys give me a second, I open here again. Yeah, I can see it here. Well, here we go. I guess you all can see this now. So just in terms of the thermal petrophysical properties, we see that the alteration in both cases, here in the granites and here in the mafic ultramafic rocks. When you have more altered rocks, you have more porosity in both of the cases, and also then your thermal properties like the thermal conductivity reduces together with how do you increase the porosity, you reduce the thermal conductivity, and that's a very important a parameter to define a geothermal resource. Now, the same happened here with the density. Now, we saw before that different types of rocks have different density, but also now inside of the same type of rock, the granites here, as you increase the porosity, you reduce the density, and the same happened here with the mafic ultramafic rocks. And a series of other parameters here also have, if you look at the P wave velocity, typically increase as you decrease the density, specific heat capacity increases as you increase the porosity, and this is now being investigated. This is what we are working right now. This is the last slide then. Perhaps I can do bigger. There we go. We only have two data from permeability that we are doing confining pressure, and we can see that the network of the pores, now they really influence how the permeability can be preserved with depths. Now here's the confining pressure going almost up to 60 megapascal, and here's how the permeability is being reduced in the granodiorite that have very nice and straight fractures. We can see that up to almost 500 meters, you have a really high permeability that is very suddenly close. This means the cracks are being put together. You have nothing more there left. Now look how different it is in the cataclastic granites. Now the permeability start quite lower, but doesn't really reduce the same order of magnitudes that you can see reducing here for the granodiorite. Now, at almost 2 kilometers, we're gonna have still a permeability in the order of minus 15 or 1 millidarcy, which, as we saw before, it's not the worst situation. Now, like we see in this graphic here, if we have permeability in that order together with the permeability of the faults, we might have advection. And this is what we're looking at. I'm very curious to see the results of the altered granite, and this is something I would like to share in the future. But yeah, I'm very sorry for what's happened in the presentation there. I don't know, but just some highlights now from this talk. The coupling of fractures in mineral dissolution. This is one of the main processes that we can see that can enhance the permeability of crystalline rocks in many orders of magnitudes. But also now when you have fractures in mineral dissolution, it can impact other critical geothermal parameters. For example, the thermal conductivity, the heat capacity, the porosity, and the density of these crystalline rocks. Now, it's a completely new field of study that we should be looking with more attention. With that, I would like to then close this talk.
Thank you, Alan.
Are you still there?
Yes, yes. we are still here. And I don't know where Camila. Okay. We have some question for you. Thank you very much. And gracias a todos. Y Camila les va a hacer las preguntas.
We can't hear you, Camila.
Now?
Uva.
Okay. Firstly, thanks, Alan, for the excellent presentation. It's an important and interesting topic, and you gave us a detailed explanation of all its aspects, really. Thanks. I will read the questions in the chat. Reitero que si alguno quiere realizarlas, las puede escribir por el chat o levantar la mano y se les habilitará el micrófono. I have a question for you. How can you get energy from such low temperature systems? Especially
That's
in
really
Finland,
nice to know.
In Finland.
Yeah, we're like in Finland now. If you see this shallow geothermal systems, we're talking about water in 7 degrees temperature, and I would drink cold water 7 degrees, not heat up my house. But this is not how technology works. Now there is a geothermal heat pumps now that you need to use a certain amount of energy to extract that heat from the water. Now, even at 7 degrees, you can take the heat, and then you reduce. If you reduce the water temperature from 7 to 5, for example, you have energy. Now, that energy can be extracted, and it's a principle of thermophysics, now thermodynamics, that the heat always go to the coldest fluid. Now, this is what they use in a heat collector. Now you need to install a heat collector there. and the efficiency of that heat collectors use, it can be like more or less a 3-to-1. If you can be even 5-to-1 in some cases. If you put 3 kilowatts of energy, or I'm sorry, if you put 1 kilowatt of energy, you're gonna get back 3. So this is already an efficiency of the system. But of course, it would be really nice if we can drill here in Finland and get water 150 degrees. No, I don't know how deep we're gonna have to go. Probably 130 meters, maybe a bit more, or 6 kilometers or 7. Our colleagues there probably can say a bit more about that. I can see some of them here. But that's the way. We have heat collectors in the boreholes.
Okay. Diego Cataño asked about what kind of logging tools can we run in the wells, if any? Do you have temperature profiles in wells with cores where you see the different types of intrusive?
Yes, the logs are very as the same in the classic or the conventional geothermal industry and in the petroleum industry. They are very useful, and that's a really nice question. Because our group, we have a very well developed team that work collecting a bit more advanced temperature profiles using the DTS measurement. They run a fiber optic cable inside of the borehole, and they can induce, the electricity. They can induce impulses in the borehole and take the message back. It's a much more reliable. Not just the type of rocks we can see, changing, but also we can see where is the fracture zones. If we have an increase or a decrease in the temperature, that means that you have groundwater inflow. And this is one of the tools that we use to define the fracture zones. But then, if you have a borehole imaging, like OBI, for example, acoustic image, that is an amazing tool that you can compare with actually you're seeing in the geophysical logs. And then if you have samples like we have in Colisma, you can measure in the lab, and then you start to make a really sweet model for where is the most promising zones. As I mostly show here in the Colisma boreholes, we are working with very small scale, core scale, but it would be nice if we actually have the data where we can make production tests from these different zones. If we could we can actually do that with packers. We can isolate the fracture zone we want to measure, and then we pump, and you can see how much water is circulating in that fracture. Now, this is a work that have to be done. There is a couple of publications we will see now, but in crystalline areas, it is very scarce. Just starting to scratch in this deeper geothermal exploration now.
Okay. Lorena Caviglia asked about, is there any deep geothermal system operating in crystalline settings? How much energy they can produce?
That's a good question. It's a lot of things in development right now. In Finland, there is a single borehole that is deeper than 1,000 meters that's been produced. Unfortunately, we don't have the amount of energy, but as I showed before by the models, usually if you don't have the increase of energy by circulation or by advection or convection, one borehole of 3 kilometers might be able to produce about 1,600 megawatts per year. This is something that we can take from a borehole. But like in a conventional geothermal area, very high temperature, a field can produce like 2 megawatts of continuous power, and that is really a large amount of energy. There is one system in construction that we're really following up with the guys in the UK. It's called the Eden geothermal project, where they drill into a fault zone, and there is 2 wells. One well they just finished to drill the second one, and they aim to inject water in the fault zone in one well and extract in the other one. And also there is one of these more sophisticated AGS systems being constructed in Canada that they have several boreholes that are interconnecting, and they promise to deliver 2 megawatts of energy. And as I say, it might be able to do it, but I want to see how much it's going to cost. That's what we're looking at. You know, increasing, again, we need to increase the reward. We need to find how to take more energy from the system at the same time that we decrease the drilling costs. You know, that's what is killing us. We can drill. Even here in Finland, we have 2 boreholes that drill down to 6 kilometers, and they enhance the permeability of the rocks. They could create the cracks. The problem is that as soon as they release the borehole pressure, the cracks, they went back together and the permeability got reduced. So this is what we need to try to find out. How can we keep that permeability there to increase the reward? But we, with systems like those that we call duplex, we can produce now up to 1 megawatt. You know, that's what the model's suggesting.
Julia Cabrera said, okay, very interesting talk, thank you. Have studied the possibility of performing hydraulic fractures as in oil. Is not so ordinary granite for greater porosity connectivity.
Yep. Yeah, this is what I call enhanced geothermal systems, and it's being a lot of research being done on that. You know, the message that I have this have been done in the oil industry for decades, and also in conventional geothermal systems. Now, they in the high temperature ones, they do cracking there as well for a long time. And even like there is not just one type of enhancement that is what we call the mechanical enhancement by creating cracks. You also can use certain types of chemical fluids and dissolve the minerals, like as you saw, naturally they occur there, but you can dissolve the minerals there. And in conventional geothermal system, they need to do this quite often. They call this acid bath. They need to circulate acid inside the borehole to start to eliminate the precipitation of calcite and silica that the boreholes start all to clog. But the only systems that I know that have been working, they already target fault zones that with existing permeability. Now the permeability was there, they just enhance. Now I don't know any system that the rock was, like they say, hard rock, hard and hot and dry. They used to call that. Mm-hmm. But that system that take a rock that there is nothing there, I don't know anyone that have been succeed at the moment. Mm-hmm. The ones like in the geothermal fields in France, they usually target the fault zones and they enhance the permeability by increasing the pressure, and also they create several earthquakes. So they are having troubles with the government now. Some of the fields was shut because of the earthquakes of magnitude like 2 or something like that. And I don't know exactly the number, but I lived in New Zealand for 12 years now. Earthquakes of magnitude 4 is just normal, all the time happening. And an earthquake of magnitude 1 or 1.5 can be created by an explosion in a mining site or even a truck passing. So there is a concern about seismicity, and that's really important that we understand that, But we need to put in the scale what's the benefit that we have. How many geothermal systems, how many petroleum systems have been enhanced for so long, and what's the problems that have been causing? Now we need to study better that to, again, decision makers, they have that tool. Yeah.
Yes. Gustavo Deep asked it about, is there any improvement benefit with the modeling enlarging bit size?
For drilling, I guess, huh? Yeah, there is several drilling, not just the bit size, but the geothermal well first, you need a bigger well than the petroleum well. We need about 12 inches. That's the size of the drilling. Mm-hmm. And then imagine 12 inches is a a borehole, and to drill that large one, it does cost much more, and also it takes much more time. Some of the drill holes, they need to change the drill bit. I don't know exactly how many meters, but quite often. You know, they need to drill because they are drilling into granite rocks. And if you take quartz, for example, that have a very high hardness, it destroys your drill bits very quickly. There is other technologies that are coming, like this plasma drilling is a huge promising, where they pretty much melt the rock, you know, and that one is promising that we can go to 10 kilometers, you know. So all things that we're gonna see in a couple of years, if they will make it economical or not. Again, everything, we have the technology, we just don't have the economics play in our favor.
Okay, Julmar Toralde asked about, you mentioned enhancing and advancing geothermal system and fractures, improving geothermal reservoir capacity. Is hydraulic fracturing allowed in Finland, and has it been done before?
Yes, we had this system here that they drill 2 boreholes 6 kilometers, and they haze the system, and they monitoring the earthquakes during all the operations, and it was very low. Now I can see my colleagues here actually that work in the project. If they want to stand up and say how much magnitude was, I don't remember, but they could see the fracture system developing by the geophones. So it's a very beautiful area. But you need to apply for a permit, you know, and you need to monitoring, you know, this. As I say, Finland has just one deep borehole that is in operation right now, and it doesn't is a closed loop system. It doesn't use fracture, didn't haze. We have just one case where the government allowed to produce this cracks there. Unfortunately, the system didn't work, and it was damaged, not commercial, the beginning of this year.
Okay, Diego Cataño asked about monitoring. Do you do any kind of temperature monitoring in the wells over time?
Yes, this is something we're really developing more and more. Now we have in that borehole field that I showed, boreholes of 300 meters now. There's 6 of them with permanent monitoring. Now, and the results now, again, between the modeling and the observe, it's really good. It's showing that the models are giving us good tools. There is an attempted of one borehole to keep a permanent monitoring there in a deep one, but unfortunately the cable broke and we don't have that operating right now. Now, the answer is only for shallow geothermal systems. If I'm wrong, I ask again one of my colleagues there, please write here in the chat if there is any permanent borehole monitoring in deep environments here in Finland. But my answer is no, just shallow. Okay.
Julmar said you also mentioned multiple drilling problems in the well you drill. How much contingency budget is typically included in your project economics for geothermal wells in Finland?
So we are a research institution, mostly. Like we can work with commercial projects, but mostly we work as advisors. No, like who make the financial of the wells usually is the company. Now that is contracting us. We can have some influence on that. No. But I confess to you that I never work in that space, you know, in the economics, trying to provide a contingency budget, you know, for how much you will, you know, you expect to expend more than the forecasted. Unfortunately, I don't have that answer for you.
Okay, Marta.
Bueno, muchísimas gracias, Alan. Thank you very much, Alan. I will make a question that is regarding to our future as oil, petrophysicists, oil workers. So my question is, can geothermal energy replace oil and gas? What is its role in the energy transition?
Yeah, it's a bit of a shoot in the feet, you know, I will say, but very importantly, you know. So at the moment, like, we don't really have any technology that can, like this, replace oil and gas. We need to make the best use of oil and gas. Why? Now, because it's such a high density energy that you can easily comparing with, for example, geothermal, you can produce hot fluids, but you can't put hot fluids in your car, or you can't move it around so well. You need to convert into electricity. Now, or like in Finland, for example, you have a market where you can use the geothermal energy to heat up the houses. 26% of the energy go for space heating. That's where geothermal energy can straight away start, to help with the decarbonization. No, but completely replace. Now, this is something that at the moment we don't have that tools. Now, mostly because the uses of oil, they are so cross-disciplinary, they go for so many areas that we will need geothermal energy, we're gonna need hydrogen, we're gonna need more wind power. All of this renewable energy technology, they need to come together to replace oil and gas. And that's the reason that we need to use the oil and gas we have now, to help us with that decarbonization. We see that is 100-something years, and then we don't have it anymore. What's going to happen if we exhaust it and we didn't create anything to replace it? So it looks like we are in more troubles than solutions. I think it's very difficult that we can completely substitute oil and gas with geothermal, but we can complement it for sure.
Gracias. Sí, iba más dirigida también a los jóvenes profesionales, the young people, para que también piensen que hay otras posibilidades de trabajo. Young professionals has a new world of work where they can work in the future, like geothermal or non-oil industry, or non-oil petrophysicists. So thank you very much.
If I can just give a comment on that, Marta.
Sí.
I think this is something I try to pass in this presentation, that there is a huge field that is opening now more and more, and we need more people, especially those that understand about petrophysical properties of the rocks. We need these guys looking at different alternatives. Now, there is a market that's growing. Now, 10 years ago, didn't have any market. Now there is much more jobs now appearing, and hopefully we will make it more profitable. Then it will have a bigger market.
Mm-hmm. There was somebody with a hand. Tamires.
Yes, Tamires.
Yeah, it's me. I am Tamires. I'm from Brazil too. I was researching about geothermal systems here in Brazil, but the capacity of Brazil is low enthalpy. And I tried to develop some system to use this, not to use it on buildings, to heat buildings, but to produce electricity. And this is there is not so much studies about this. And there are regions in Brazil we don't have hydroelectrics, but we have thermoelectrics, and they show a high heat flow. And I think it can be a good and interesting place to explore, but the university don't see many perspectives for Brazil for use geothermal. And I would like to know your opinion about this.
Yes, I think, as you mentioned, Brazil is in a low enthalpy condition or low enthalpy setting, but it's much higher than here in Finland, I can guarantee you. There is areas in Brazil that the heat flow is much higher, as you mentioned. And there is 2 branches here that Brazil should be taking in terms of research. Now, one branch is the electricity generation, that for sure, but you need high temperature. Now, even with binary geothermal plants, where you have one working fluid that is much lower temperature for boiling, No, that you need to boil in there. Even in that, even in that binary systems, you need at least, you know, if it's 70 degrees, there is someone coming and talk here.
Exactamente. Yo esta mañana abrimos toda la casa.
Por favor, pueden
Pero
cerrar.
ya ahora, ya viste, ya hace un calor que ya.
Are you muted, Alan?
Yup, back. This binary geothermal plants now minimal 70 degrees, and to make it efficient about 120 degrees of temperature of the working fluid, now the water, which again, you know, start to make it challenging. As you go deeper in Brazil, same problems with permeability. That's one branch that need more resources. Can you find fault zones where the temperature will be higher now, and you can find water about 100 degrees? Then the problem is that Brazil going to compete with cheap electricity from the hydroelectrics. Now, to install a geothermal plant is a lot of money, you know, and then how are you going to compete in terms of price of electricity? We know that we're starting to have more problems in Brazil with the droughts. You know, we just don't have water enough, and we need an alternative. So that's a lot. Again, it's not a market; it's a line of research that should be invested. But I think that something that could be very quickly done in Brazil is to use the opposite of the space heating that we use in Finland. The same principle that we do here for warming the buildings, you can use for cooling the buildings. Now, and that could be done, you know, quite efficiently. We do believe in that. We need more examples. I think there is one project ongoing in USP now that they create this geothermal system for, yep in USP.
But they are developing for each area here in Brazil. Do you know?
They are doing there in university. They are cooling their own building.
They are researching, but in each area, São Paulo, Rio de Janeiro.
In São Paulo, in the USP University, yeah. This is how much I know, but I think that is a field that could take over quite quickly. And as I show in Finland, you know, the market starts and boom, you know, the companies, they took over because it's easy to do, it's profitable, you know, and it's you don't need a large amount of investment comparing with the amount of investment that you need for power generation. So I really think Brazil should look at that, because the air conditioner bills are huge there in the country. You know, it's a lot of energy going to cooling, and we're going to need more and more cooling. So
actually, what happened is it's a proposal for a research, and they didn't like the proposal, and because they wanted to product a thing, not a scientific research. And I said to them, maybe we can produce something we can sell to the world or other things to other countries with the similarities with Brazil. And I don't know your opinion. We can talk later about this. And I would like to know, because I am a reservoir engineer, and I study everything, and I make some math models, but there is a question about geological modeling about these places. But I have some powerful math models to apply to this kind of reservoir. If you wanna, I can share with you.
That would be lovely. Thanks a lot.
Yeah.
Thank you, guys. And sorry, but we don't have more time. But an amazing presentation, really. Alan, thank you again for his presentation, for your presentation, and the presence of all. Nuevamente, bueno, te agradecemos, Alan, y la presencia de todos. y de las hermosas preguntas que se hicieron, pues la verdad sumamente interesante.
I think that's
Bueno,
the aim, is to create a discussion now.
yes,
Let's go
that's
to the
wonderful.
coffee break and have a
Sure.
matcha and talk with people around. Yeah.
Bueno, agradecemos nuevamente a nuestro disertante, que para nosotros es nuestro distinguished speaker, y a todos los presentes. Y bueno, si se quieren contactar y continuar las discusiones por mail, se pueden contactar con el doctor Alan Bischoff y yo les paso el mail. Este va a ser nuestra última reunión del año. Muchas gracias, fue súper rica, se pasó volando. Empezamos justo a las 10, son 12:30, tenemos que cerrar la sesión, así que muchísimas gracias por el interés. Muchas gracias, Alan. Thank you very much, and we see you next year. I don't know where.
Ahora.
Es la hora de almorzar. Thank you very much.
Muchas gracias.